In this video, I want to talk about powers of the transition matrix. If we have a Markov chain with an initial state of x0, then we know x1 is equal to p times x0. We know x2 is equal to p times x1. And p times x1, or x1 is p times x0. So this is p squared x0. x3 is p times x2. Well, x2 is p squared times x0, which is p cubed x0. And we can continue this process. In general, xk is going to be equal to p to the k x0. So once I know my initial state, I don't have to find each intermediate state like I have been doing in my previous videos. I can raise the transition matrix to a power and multiply by my initial matrix. So let's look at an example. Here I have a matrix P and an initial state vector, and I want to find x3. Well, we can do this by finding p cubed times x0. And I will not show out all the steps. You can use technology to cube matrix P, but you should get 0.562, 0.219, 0.438, 0.781 times my initial vector, 0.5. And if you do, you get 0.3905, 0.6095. So we can use powers of my transition matrix to find my vectors. So far, the examples of Markov chains that I've done in previous videos, the state vectors seem to stabilize after a period of time. So it's reasonable to ask whether all Markov chains have this property. Let's consider this transition matrix here, 0, 1, 1, 0. Well, a simple calculation will show me that p squared is equal to I. So that means the identity is equal to p squared, p to the fourth, p to the sixth, etc. And p is equal to p cubed, p fifth, p to the seventh, etc. So essentially, my vectors end up being x0, p of x0, x0, p of x0, etc. They're going to oscillate between x0 and p of x0. So this Markov chain does not actually stabilize unless both components are 0. Both components are 1/2. And you can verify that. So now my question is, what does it take to make one of these systems stabilize? To determine this, we need to define a regular stochastic matrix. So stochastic matrix P is said to be regular if P or some positive power of P has all positive entries. As an example, we have this matrix 0.51, 0.50. This will be regular since P squared, which you can verify, is 0.75, 0.5, 0.25, 0.5, which is all positive entries. So the main thing is we need to be able to raise P to some power and get a matrix with no zeros, only positive numbers. And it turns out if I have a regular Markov chain, I have a regular stochastic matrix, then I will get what's called a steady state vector. A vector that eventually I will always output. A vector such that PQ is equal to Q. And this is my steady state vector. It's essentially what's eventually going to happen and how we eventually stabilize our system. Since we do have this condition that PQ is equal to Q, that tells me that it's an eigenvector corresponding to an eigenvalue of lambda equal to 1. So we can find Q, we can find our steady state vector by solving the system P minus I, because normally we would do P minus lambda I, but lambda is equal to 1 in this case, times Q equal to 0. So let's look at an example. Let's go back to this matrix here. Since all the entries in P are positive, the Markov chain is regular. So let's solve P minus I, Q equal to 0. So we start by subtracting 1 from the diagonal. 0.8 minus 1, 0.1, 0.2, 0.9 minus 1. We can add the two rows together to realize that this is 0.20 in the first column minus 0.10 in the second column. So my equation says 0.2x1 minus 0.1x2 equal to 0. Or 2x1 is equal to x2. So that means Q we know that x2 is equal to 2x1. x1 is just x1. We don't know anything else about that. And so to find a probability vector, we need to find the value such that x1 plus 2x2, if I add the columns, they should be equal to 1. Or 2x1, sorry. So we have 3x1 equal to 1, so x1 needs to be equal to 1/3 in this case to have a proper probability vector where things add to 1. So my vector will be 1/3, 2/3.